Go. Perfect. Thank you, everybody. This is the April 2023, good grief, session of the Microsoft High Availability Data Platform Continuity Group. We have Kevin Feasel with us, Microsoft Data Platform MVP and Engineering Manager of the Predictive Analytics team
Not
at
anymore.
Shuttle. Oh,
Sorry.
no.
No, that's old.
Whoop. And go ahead and introduce yourself. Go for it.
All right, welcome everybody. Yeah, my name is Kevin Feasel. As Mr. Clee said, I am still a data platform MVP. I'm out of Durham, North Carolina. I'm now actually a full-time consultant doing my own gig with Catalyxy Services LLC. And I also have a blog called Curated SQL. The idea of Curated SQL is that I try to find and link to 5 to 10 posts per day on topics all across the data platform space. So that's curatedsql.com. But we won't talk so much about that. I know that I did jump into my spiel, but I wanted to jump back and see if there's anything else on your mind, David.
Oh, you're good. No, I just wanted to introduce the title. It's Optimizing Backup Performance Using Data Science Techniques. And I got to tell you, I am thrilled to see this, partly because I am one of those weirdos that loves optimizing backups, and especially when you're dealing with very large databases. So with that, I will turn this over to you.
All right. Well, thank you. So yeah, we've already done the spiel slide of who I am, what am I doing here. Maybe we haven't figured out what I'm doing here, but hopefully we'll get to that somewhere during the talk. So the impetus behind this session, by the way, if you have any questions, any thoughts, anything you want to mention, put it in chat. I have chat right in front of me. I'm actually looking at it right now. And so if there are questions, I'll take them whenever I can fit it in. Exactly. Woohoo. So how big is your backup window? This is sort of the impetus behind this talk. And the question is, how much time do you have to perform those full backups? So I'm going to focus mostly on full backups as opposed to differentials or transaction log backups, just because that's usually the most interesting problem of the set. And my goal is to apply some data science techniques to minimize the amount of time that it takes to back up those databases. And this way, we could potentially back up and restore databases significantly faster than what the defaults allow. So I'm going to take this one step at a time. Our first step is describe the problem, try to understand what it is that we're trying to solve here. Then we'll do a little bit more. By the way, my slides are all over here, so if I keep looking that way, that's the reason why. So backups and also restores. I can't say backup without saying restore. It's actually in my contract. But these are critical for database administrators. And it can take a long time to back up a large database. If we're talking terabytes of data, we may be looking at hours and hours of time to take that backup. And if my backup window is 6 hours, that's all I get to take those backups, then we run into trouble as those databases get larger and we start having to make compromises. So the question is, well, what can I possibly do about this? And the first thing is we could use read-only file groups. With read-only file groups, we know that the data is not changing, so I don't have to take backup after backup of that data. And if it does change, we set it to read-write. We make the changes to the data. We set it back to read-only. We take another file group level backup, and that data's done. Newer editions of SQL Server, since at least 2017, there were a lot of changes in there that just made backups a little bit faster. I believe 2019 had some changes as well. So upgrading to newer versions of SQL Server can potentially improve your backup performance. The less data that you have, the faster your backups are. I don't think this is a mind-blowing discovery from me, but if you have tables that are obsolete, that are just sitting around, there may be some very large tables which are totally unnecessary. And in that case, dropping them would free up enough space and reduce the size of backups. If you're not already using data compression, row level, page level compression can reduce the amount of data written to disk. Data written to disk is data written in backups. Similarly, column store indexes, if you have fact style tables, meaning a lot of data, mostly numeric and date types, no strings of any significant length, then we might be able to use column, and also the access pattern is that you're doing aggregations on that data. But if your table fits those patterns, then switching over to a column store index, like a clustered column store index, could significantly reduce the amount of disk space that is required for your table, and again, make backups significantly faster as a result. If we're splitting data across multiple file groups, then we're going to be able to back up those file groups separately, sort of like read-only file group, except that I'm going to have to continually back those up. But I can back those up and decide that, well, today I want to back up this database and I'm going to hit these file groups all at once. And then next day I'll back up this other database and I'll hit different file groups and just try to spread out that load as much as possible. I did mention that I wouldn't really dive into differential backups, but that is a possibility. And I should also mention that there are things like I can use snapshot level storage backups if I go into that world. I'm definitely not an expert on that topic, so I'm just going to mention it as a thing which exists versus a thing that I'm really going to talk about. And we could configure backup settings. So there's a whole lot of stuff that we could do. I'm only going to care about this last one. Everything else, I just mention it to say, hey, these options are available. You should look into them. We're not going to talk about them because we're going to spend enough time talking about configuring backup settings that, trust me, we'll be done with this session. It'll take a full hour. So let's talk a little bit about those backup settings and see what we're getting ourselves into. So I want to back up a database. That's easy. I open up Management Studio or Azure Data Studio, new query window, backup database, Scratch, or whatever the database name is, to disk, and I write it to a disk with no format and init. Basically saying if you already have a scratch.back there, wipe it, replace the header contents with whatever new contents you need, replace the data contents. I'm not going to try to have multiple databases or multiple database backups in that .back file. No big deal. It writes out a new file probably called scratch.back. If there was a file there already, replaces all the contents. And that's not the only thing we can do with it though. We can, of course, change different values, like say block size. So block size is the physical block size, and it ranges anywhere from 512 bytes up to 64 kilobytes. That list in the middle is the complete list of possible values. So 512 bytes, 1K, 2K, 4, 8, 16, 32, 64K. Now, if you're using certain types of media for backup, like if you're writing directly to tape or you're burning a CD to CDRW, then block size matters a whole lot. It doesn't really matter that much if you're writing to disk or writing to a SAN or a NAS. So I will give you some free advice. If your backup strategy is to write backups directly to CDRW, you can make it a lot faster by not doing that anymore. Otherwise, block size is probably not going to do much for us. So let's next talk max transfer size. Max transfer size, this is the maximum amount of data we can transfer per operation. And over on the far right-hand side there, I've got all the possible values, 64K up to 4 megabytes. So this is a list of exclusive values. We can't say 65 kilobytes. It's 64, 128, and so on, up to 4 megabytes. I like to think of this as a metaphor as like a bucket. So this is how big our bucket is. This bucket is 4 megabytes. This one is 1 megabyte. And along with max transfer size, we also have buffer count. Now, buffer count just has to be a natural number. So 1 or some integer above that value. Well, this is the number of buckets that you have of size max transfer size. So if I have 2 megabyte max transfer size, I have 100 buffers. That means that I am allocating 200 megabytes of RAM for the backup operation. If I have 1,024 buffers and 4 megabytes, that means I have just allocated 4 gigs of RAM to take this backup. It doesn't mean SQL Server is necessarily going to use all 4 gigs, but I have to have that available in case it wants to use all 4 gigs. So my advice, try to stay at or below 1,024 buffers. I'll give you better advice as we go on, but basically, adding more buffers doesn't necessarily make backups faster. However, it does take a bigger hit on your total utilization of RAM. And if I were to tell you that you're backing up 5 databases at once and you have 4 gigs per backup in terms of RAM that's required for that backup, and said, well, I'm going to take 20 gigs of RAM from your machine in order to do these backups, you might say, I'd rather have those 20 gigs or a majority of those 20 gigs for my buffer pool or for memory optimized tables, for whatever else that I may want to use it for in SQL Server versus just having to have it be available for backups. So that's our opportunity cost. That, yes, I can add more buffers. It might make the backup faster. It's going to take away from my next best alternative for that RAM, which could be adding more into the buffer pool and having fewer reads from disk. So the other option that we can set is file count. File count essentially says stripe my backup across multiple files. And it's a good way of getting extra throughput out of your files. And again, this is a natural number, 1 or above. Quick recommendation, somewhere between about 1 to 12 per drive for direct attached storage and about 1 to 12 total for a SAN. 12 may feel a little excessive, but there are performance gains even if you have multiple files writing to the same local attached storage. And so it's kind of interesting that we're not say trying to push on a string here, that there actually are gains from having 2, 4, 8 separate files written to the same disk at the same time. Finally, compression, true or false, whether or not you want to compress your backup. So compression, typically, I will recommend yes. There are certain exceptions, like if you're on specific CUs of SQL Server, of various versions of SQL Server, and you're using transparent data encryption, then there have been problems. There have been bugs that, granted, have been fixed for a couple of years, but there were bugs around. I have transparent data encryption and I have backup compression. The backups that I'm taking actually don't work. They don't restore correctly. So make sure you're patched to the latest CU of SQL Server, whatever version you're on, and it should work fine. But I did want to call that out as a caveat because there have been bugs in the past regarding the combination of the two. Also, if you're using third-party software to take backups, then they may offer their own form of compression. Just something to keep in mind. If I'm assuming that you're taking native backups for the purpose of discussion here, and in that case, typically my recommendation is, yeah, go ahead and compress. You're going to have less disk utilization, and disk utilization tends to be the bottleneck for backups rather than CPU. Your mileage may vary, but we're coming up with some new settings. So now I've still got backup database scratch, but I'm going to write it to 2 separate files on the same drive. I'm still with no format and init, but then I said, okay, I'm going to use 2 megabytes max transfer size, 50 buffers, 8 kilobyte block size, turn on compression. And so I've got some settings, and these settings look good. I'm like, hey, they're certainly looking better than what the defaults were. In case you're interested on the defaults, that does change over time depending on which version you're on of SQL Server. But the historical default is, if I remember right, it was 7 buffers and max transfer size. Oh, I'm gonna lose this trivia contest, but I believe it was a 1 megabyte max transfer size. So 7 buffers was the default. Now on newer versions of SQL Server, depending on your database size, the buffer count will change. Still, I have some number here that it kind of looks reasonable, and you may ask, so what values should I choose? Are those the correct ones? And the answer is, I have no idea. The correct answers are going to depend on your hardware, your circumstances, your workload, specific to your environment, whatever factors may be there. How heavy is that workload during your backup window? Can you just take a backup throughout the course of the day? If so, You've got this 24-hour backup window, but maybe you want to minimize the impact during that workload or during that backup. Alternatively, you may say, no, I have this fixed window during which time I can have those maintenance tasks running, but I need to get that done within 4 hours. And during that time, maybe it's reduced workload, or most of the people are at home, are asleep. Sorry about that. Zoom crashed. So let me pick back up where I left off.
No worries. It was brief, so you're good.
Okay. So, yeah, like I was saying, this is all going to depend on your circumstances. And what I can do at least is I can't give you the answer for your environment, but I can at least tell you, here's how we can figure out what the right answers should look like. And in order to do that, we're probably going to have to do a little bit of sampling. And here's why. I've given the set of block sizes and max transfer sizes. So those are fixed sets. We have, if I do my my zoom it math, so I've got 8 values for block size. I've got 7 values for max transfer size. Now let's say that I pick these as my available numbers of buffers. We already know I can pick any integer value that I want, but capping it at 1024 for sanity purposes and picking some arbitrary numbers, starting with 7 because that was the SQL Server default. Going below 7, you're probably not going to do better. So I've got 8 values there. And for numbers of files, I decided I'm going to pick even numbers plus the number 1 because 1's the default. So I've got 7 there. And compression, I'm just going to say true. I'm not even going to try it without compression. Well, if I do 8 times 7 times 8 times 7, that's 3,136 separate options that are available to us, combinations. And if it takes me on average 10 minutes to back up a database, that's about 22 days straight of backups to figure out the right answer. And if it takes 10 minutes to do your backup, I mean, you're probably not even that concerned. We're talking more about it's taking 8 hours to do a backup. And in that case, 3,136 times 8 hours is a whole bunch of hours. So potentially we could sit there and just take one backup after the other for however long it's going to take, do all the math and find here is your best combination of settings. But we don't really want to do that. And fortunately, we don't need to do that. You see, we can do a little bit of sampling, and I see Andy Levy in here, so I'm going to call out DBA tools because, yeah, I did use that for the purposes of the demonstration. But we can do a little bit of sampling in PowerShell and say, I don't want all of these options. I can get a tiny fraction of the total work, but it'll still give me enough data that will help me speculate on the end results. So let me take a quick look at that. First, I must find my script, and here it is. So let's increase that size a little bit more. I will share the links to all the scripts and slides and everything at the end of the talk. But for the moment, we're going to import DBA tools. And then here's a function that I grabbed from somebody else to build a Cartesian product. I will want to build that product of all of my possible combination of values for block size, for buffer count, max transfer size, for number of files, and even for compression. In this case, I'm going to pick an instance and a database name, and I'll say, okay, give me my Cartesian product of block sizes, buffer counts, max transfer sizes, file counts, and compression. So for the demo, I do have compression on and off. And that gives me approximately 10,752 viable results for these options. So if I want a relevant sample, I might take maybe 100 database backups. 100 is a decent number to start with. It's probably going to give us a fair number. Like I can imagine I'm going to have roughly 12 entries for each block size, roughly 12 entries for each buffer count, 12 to 15. So I'll have about 12 to 15 copies of most of these. I'll only have about 8 copies of different file counts. But with this, it's still enough that I can probably get started with an analysis. I don't think I'd want to do many fewer than 100 samples for a database, given the set of viable options for me. I want to have, ideally, I'd want to do more like 300 or 400 samples. But knowing that a sample is still a full database backup, this is still going to take some amount of time. It's just going to take about 1% of the amount of time that it would if you tried to do a full search space. So the way that we're going to do the sampling is I'll get a random number, maximum of 100, and get random in PowerShell returns an integer that ranges from 0 to the maximum -1. So it's going to range from 0 through 99. If my random number is equal to 99, essentially, then I'm going to take a backup. The thing that I will point out about get random is that get random is uniformly distributed. And what that means is that if I draw a little graph of all of the different values ranging from 0, 50, et cetera, up to 99, I would assume that if I pulled enough of these, if I ran get random 10 million, 20 million, 30 million times, the likelihood of finding a value that's like a 1 is the same as a 2, is the same as a 3, and so on, so that the probability of any of these values is equal. That's relevant for us because what that means is I can just say, if I want 1% of the data sampled randomly, cool, just give me that slice where it's equal to 99. And I don't have to worry about, well, the things that have a value of 99 are heavily distributed with certain block sizes. I mean, that's not true. It's all just shuffled randomly. So I can take advantage of that fact and essentially assign each option as a random number on that uniform distribution. So then I can say, okay, well, given that entry, given that I've generated a random number, and if that random number is 99, I'm going to take a backup. If my entry tells me to compress the backup, then I'm going to call backup DBA database and send in the SQL instance, the backup directory. I'm going to give the database. The type will be full. It will be copy only. I will compress the backup. My other settings, I can set the buffer count, the file count, the max transfer size, and the block size. The only difference here is if I don't compress the backup, I'm not compressing, and I don't have that option for compress backup in here. So this is my script. And then what I decided to write out was block size, buffer count, max transfer size, file count, compression, and the number of seconds that it took. So I'm doing that, and I'm writing this to a file that's performance-test.txt and deleting my backups afterwards so that I can have a fair comparison. I did back it all up to g:\backups. Obviously, if you were to try this out on your own, you'd probably want to change this to the appropriate location, whether that be a UNC share, a local disk, or whatever. So also made the assumption we're only backing up to one drive. If I had multiple drives, I could have further experiments there, but I only had the one drive to back up to. So what this gives us is some small percentage, 1%, 2%, somewhere there, of the total search space. But I forget if I have a nice picture of it. If I don't have a nice picture, I'll draw a really poor picture. But with that sample, we're still going to be able to find what is a reasonable solution. And that's what we're going to get in the analysis section. So we want to do an analysis. Might want to ask ourselves, well, what kind of problem are we solving? What we're solving is called a regression problem. Regression is a form of supervised learning. Supervised learning basically says, when I train a model, I know what the answer is already, and I can figure out, here's my inputs, here's what the model expects the answer to be, and I can compare it to the real answer. I know how long that database backup took because I calculated that. That's part of the PowerShell script output. And I have my inputs, the things that I believe control how long it took to back that database up. the things like buffer count, max transfer size, file count, compression, and block size. So knowing those inputs, knowing that output, the real output, when I train my model, I get predicted outputs. What I'm trying to output is a value. And that value is how long is it going to take to back up that database? So this, because I'm trying to predict a value and I know what the answers are, is supervised learning and regression. There are several examples of ways to solve regression problems. So linear regression is one example, random forests and CART, which is classification and regression trees. Another example, neural networks, yet another example. As far as linear regression goes, it's pretty straightforward. This is the thing that we get in stats class. It's the thing that we spend a lot of time talking about because it's really easy to understand intuitively. We have some notion of an explanatory variable or our inputs, and we have some notion of the response variable, the output. So our inputs in this case, our explanatory variables, we assume are things like block size and file count and so on. Our response variable, the thing that we want to predict, is time taken to backup. Here's an example of GDP, gross domestic product, that's used using purchasing power parity to drive everything to 2005 US dollars. And it's plotting countries and life expectancy over time by continent. So each of the dots represents a different continent. Each of the dots represents a country. The color represents the continent. And the gray line represents the model's best interpretation of how to read this data. So essentially, it's what we're trying to do with linear regression. Now, with decision trees, we know of a decision tree as a series of if-else statements. And CART is basically decision trees, except at the bottom of the if-else statements, we're returning a value. So in this case, if my database size is less than 50 and memory usage is less than 32 and file count is less than 10, then here's my prediction. But if file count is greater than or equal to 10, here's my other prediction. And so we break this out into a series of if-else statements leading to an answer. Well, that's a decision tree. Random forest is basically you take a bunch of these decision trees, get them all together, and have them vote. So for some of the trees, we might only provide them some of the features. You don't get to see buffer count. You don't get to see number of files. Or we may slice to a certain subset of data. You only get to see these 40 rows. And we build a whole lot of these different trees and have them each vote and say, okay, given this new piece of information, what do you predict it will be the correct answer? And if we have 1,000 separate trees voting, we could take the average of those answers. We could take the median of those answers, whatever formula we need to. But we end up with a final score that is the combination of the brain trust of a bunch of dumb models. And it turns out that works really well in practice. So that's random forest at a very high level. I don't get into neural networks in this session because we're not going to use one. We could talk a little bit about it, but I would get out of my depth, especially if I'm just trying to wing it. So they exist. They can be very powerful. They may or may not be better at solving this particular problem. Your mileage may vary, I guess. So let's dive into the analysis. And if you want to try the same analysis as me, I have a Docker container that includes all of the tests for what I ran through in this case. And I also have a notebook. So inside data, we have all of the different tests. Inside notebooks, I have my one notebook and an R package. So this data came from 3 separate databases. BAC, which was actually a real customer database. The full customer database size was 89 gigs. And then I took off the biggest table, I just dropped it, and it dropped down to 57 gigs. And then I dropped the next biggest table, and I dropped, it started at 136, and then it went down to 89, 57, 31. Stack Overflow, the 2010 edition was about 10 gigs, and the 2013 edition was 50 gigs. I did try with a more recent version that was several hundred gigs and actually ran out of disk space trying to back it up. So that example never got off the ground. But this is, I think, a reasonable starting point. Obviously, if you're talking about 30 terabyte databases that you're backing up, we're going to have to do separate tests for that. But this was what I had available on my machine at the time. So it's what we're rolling with. Okay, I spent a whole bunch of time talking about it. This is my summary in case you want to read this later. And if you are not at all familiar with the R programming language, here's what we're going to do. We're going to zoom in a little bit, and I'm going to say that's okay because we're going to talk through this together. There we go. First thing we're going to do is load some libraries. The tidyverse is a nice library for getting tidy data. And tidy data is a very fancy way of saying roughly third normal form, and then denormalized a bit to make it easier for analysis. So that's the long version of tidyverse. Random forest, we talked about what a random forest does, and this is a library that lets us do it. Caret is a package that helps data scientists perform common activities. PartyKit and EVTree are some fun extra libraries that we'll get into a little bit later. EVTree is evolutionary trees, and that's my favorite part of the talk. So I mentioned I'm going to use databases, 6 different sizes, ranging from 10 gigabytes to 136 gigabytes. And in order to read each of these, I'll use the reader package to read a delimited file. If I want to look at a sample, I have here no headers. So it is comma delimited. There are no headers, and it just includes those outputs that we had from PowerShell. So we're going to read them in, and we're going to assign column names of block size, buffer count, max transfer size, file count, and duration, which is in seconds. And so I'll specify each of my types as an integer column. So I don't have any decimal values for seconds. It was just whole number seconds. I do this for each of the 6 files. So let's do that now. And each one is going to be in its own R data frame. For each of these databases, I don't think anyone would be shocked if I told you that the database size does play a role in how long it takes to back up the database. So in order to help out R, I'm going to tell it what the database size was for each database. I'm also going to create one more data frame called backup stats. And backup stats is the row binding or the union all of each of these 6 data frames. So I could say head of backup stats, and it will give me, here are just the first 6 records in backup stats. And I could say in row to tell me there are 541 total backups. Remember, 6 databases, so somewhere on the order of about 90 backups analyzed per database. Not quite my 100, but it's close enough. Now, I'm also going to turn block size into a kilobyte measure as opposed to number of bytes. That way I can read it a little bit better. So if I do the head of backup stats again, my block size is now 16K, 32K, and so on. Also, memory usage. Turns out that max transfer size and buffer count are completely interchangeable to the extent that I have found in any analysis, meaning that if I have 1 megabyte max transfer size and 50 buffers, that is going to be equivalent in terms of how long it takes to back up as 2 megabyte max transfer size and 25 buffers. Basically, it's the amount of RAM that we are allocating for the task that matters, not the way that we allocate the RAM. So at least over my testing, this is what I found. And also, if you do keep these separate, the analysis will underweigh one of the 2. That's because there is, the 2 basically are 2 parts of a whole, memory utilization. And if you only look at one part of the picture, you don't get the full picture. And the model ends up underweighing their importance. Which is why instead of having buffer count and max transfer size separate, I'm going to combine them together so that this analysis becomes a lot easier. Also, we have duration, which is number of seconds that it took to back up. I'm going to create a measure of throughput, seconds per gigabyte. So how many seconds did it take to back up a database of this size? And that way we have not only the rate or the stock measure, the how long it took, but also the flow measure of how quickly are we performing these operations. That will also be important in a little bit. So we're going to take our data and randomize it. To randomize it, I'm just shuffling the data. I've got a block of 31 gigs and a block of something else, and these 6 blocks of data that are all together. Well, I want to shuffle all those results around so that when I split my data into training and test subsets, I get a random sampling of all of them. And to do that, I can use the sample function and do that across all of my backups and call that rand backup stats. So now the new data frame is going to have a different shuffling. I set a seed, a random seed, and that way, basically every time I run this, I'm going to get the same results. You can, of course, change the seed. You'll get slightly different results. But for the purposes of knowing what is going to show up on the screen, I did set the seed to this particular value just because that way, next time I give this, I can have my text results match exactly what the data results look like. If you do change the seeds, those values will alter a little bit, but you're not going to see massive changes. It's more like a percentage point difference. Next thing I want to do is cause data partition. And data partition is basically a way of saying, all right, I want to have training data, which is the data that I'm going to use to build out my model. But I also want to have some data that the training operation doesn't get to touch. This is my test data. My test data is a way of evaluating how the model did without the model having the advantage of being able to see that data first. Because what happens is by training a model, really what we're doing is we're saying, all right, here are the real answers. You're going to generate your answers and we're going to see how far off these are. And then we'll have iterative retraining to get to where these answers match up as closely as possible. Well, now we're going to give you the test, and the test doesn't, you never got to see what those answers looked like before. This is how well does this model map to new data that it hasn't seen yet? Because in the real world, when we send that model out, it's not going to have seen the data beforehand. So we want to have as close to an evaluation of what it would perform like in the real world as we can get. Knowing that we only have this one source of data, I'm just going to break it up into training and test subsets and work it with those subsets that way. So my training data will have 380 rows. My test data will have 160 rows. Basically, I split it where 30% of the data went into into the test data set, 70% goes into the training data set, approximately. In an ideal world, I want to have as much data as possible in this training subset. In a practical world, I want to have enough data in the test subset to be confident that the results I'm looking at are reasonable. And that's the trade-off we have to make. So if I had my way, I'd have tens of thousands or millions of records, and I'd be able to have 99% of it in my training data, and the remaining 1% would still be enough to give me a good idea of how this operates in real world experience. We're nowhere near that. So we do what we got to do. But briefly, a quick look at my training data. So I've got data that's across the different database sizes, the different file counts and durations and everything. And I've got, so my duration, which is number of seconds that it took. I've got my throughput measure, seconds per gigabyte. And we're going to build a random forest. I'm not even going to try linear regression. The results are not as good. Random forest turns out to be better. And for the sake of time, we're just going to go down the best route. So let's build a random forest model. I'm going to try to analyze based on duration, saying that I believe block size, memory usage, file count, and database size are the things that impact my duration. So those are the inputs, duration is the output. We're going to build 2,000 trees, and I'm going to calculate the importance. Importance will be important, strangely enough, for calling this importance function, which tells me just how useful was each of those input measures. The way to read this is percent increase in mean squared error. Basically, if this value is negative, then the random forest function says, this isn't actually useful. If the number is approximately 0, random forest says it's not that powerful. The larger the number, the more powerful, more important this feature is to describing the output. So database size is so overwhelmingly important for how long it's going to take that backup. But I think this is a very obvious conclusion. So obvious that I don't know how meaningful it is. I mean, my advice then becomes, cool, start deleting data until your backups are faster. But that's probably not going to work very well or keep your job very long. So we want to try to find something different. I mean, it does say memory usage has some factor, some importance. But how about instead of looking at duration, we look at the throughput instead? Before I do that, though, I do want to show you how well does the model do at analyzing this variance. It explains 90% of the total variance, which that sounds pretty good. It's basically for a given duration value, how much of that change in duration can we predict based on our inputs of block size, memory usage, file count, and database size? And yeah, I got 90% of that. So at that level, it sounds like a pretty good answer. At this level, taking it back to subject matter experts, people like us, we look at that and say, yes, it's obvious, but I think you're missing the bigger picture. And actually, I'm not sure I totally agree with all of this. So let's build some predictions. I'll use the predict function, given the model that I've generated and the test data that I've held aside, we're going to build some model predictions. And I'll take that test data and I'll combine with the predictions to create my outcomes. And for outcomes, let's ignore block size. Let's ignore predicted seconds per gigabyte. When looking at this, we already said in the slides, look, block size doesn't actually matter. So I'm going to take it out so that we don't have as many columns that we're messing with. But I have my predicted seconds per gigabyte. I have my model prediction. And if I look at my outcomes, this is the number of seconds that we thought it would take. This is the number of seconds per gigabyte we thought it would cost us. This is the actual number of seconds. This is the actual number of seconds per gigabyte. And so this first example, this is a really bad guess. Took 82. We expected it would take 82 seconds, but it really only took 19. This one is 201 versus 203. That's not bad. 122 versus 123. This one, 210 versus 197. I mean, it's not great, but if I'm eyeballing this, I can look at it and say, I guess it seems okay. It turns out that eyeballing things isn't really the best way of understanding how well a model performs. So we're going to do a calculation to figure out what might be a more appropriate way of determining the quality of a model. And for a regression model of this sort, there's a function called root mean squared error, which turns out to be very effective. Root mean squared error, one of the really nice things about it is the output of this function is in the same, it has the same denominator as what is the predicted value. So in other words, duration is measured in seconds. Root mean squared error, therefore, is measured in seconds. And this is saying for our predictions, we are approximately 26 seconds off on a normal prediction. So we missed the boat by about half a minute. And that may or may not be good. But given that, we're seeing the high numbers of predictions are in the 200-second range, we might have 300 seconds. We're off by at least 10%, sometimes as much as more than 100%, like in this case. So let's plot our results and see what we get. I'm going to zoom out just a little bit so that we get the entire plot on here, and I'll explain what it is that we're plotting. We are plotting the duration on the x-axis, the prediction minus duration on the y-axis, and doing this as a scatter plot. So in other words, this y-axis represents our error term. How far off were we from an actual prediction? In an ideal world, every one of our dots would be on this red line at 0. We don't live in an ideal world. So what I would hopefully expect is that our dots are basically jittering around this red line, but that it's essentially jitter. It's just random noise. What we see in practice is, I would assume that these are my different database sizes. And maybe I've got 2 databases in this range, but we can see clear clusters. So we definitely see cases where database size still has an impact on our performance. So given that, taking that in mind, let's change up how we're going to do our calculation. So for random forest, my second take on it is, instead of predicting duration, we're going to try to predict seconds. How many seconds does it take per gigabyte? And if it takes fewer seconds to process 1 gigabyte of data with some settings, then our throughput is faster. And regardless of how big that database is, lower number of seconds per gigabyte means we get done faster. So we'll take the same inputs, but we're going to try a different output. We're going to hopefully factor out database size. We'll still build 2,000 trees and calculate our importance. Here's what our importance now says. When we're looking at this throughput measure, what are the things that are important? Well, memory usage and database size, still important. It's interesting how database size, even when we factored out, we divided by database size to get seconds per gigabyte, it's still a relevant factor. Memory usage is just as relevant. File count is saying it's not as relevant, but it's still got some importance. There is still some value to file count. Block size, nah, still not important. If I take this back to subject matter person and I say, okay, we have more memory to be able to store more data in memory as we're backing it up. We have more files so that we can open up more files to the same disk and write it out. And database size is still important. I think subject matter expert person looks at this and says, this is more reasonable to me than the initial version, which was number of files doesn't matter, memory usage barely matters, block size doesn't matter. I think this looks more sane, which is a good first step, but just because it looks more sane doesn't mean it's better. So we're going to have to go through the same analysis. We're going to try to get the same understanding of how this model compares to the prior one. So let's look at that model. And we see variance explained is only 62%. Now, the first model had a 90% variance explained. So we may look at this and say, oh, second model's worse. Before we go down that road, I do want to mention, because we changed the shape of the model, we changed what it is that we're trying to predict, I would hesitate to compare variance explained directly. If we changed some input feature, but we kept the output the same, in that case, we potentially get a better feel for variance explained differences. Here, it's a different problem because we're trying to predict for a different thing. So just because this number is lower doesn't mean that the model itself is necessarily worse. That's what I'm getting at. If we're keeping the response variable, the thing we're trying to predict, the same between experiments, then we could compare variance explained and have that be a first check, a first sanity check. Like maybe I'm doing different types of trees. Maybe I'm doing different levels of what's allowed to be collected. If I have different hyperparameters that I'm working with when I generate my models, those would be the types of things where I want to see if it changes variance explained. But because we have a totally different problem, I am going to ignore this and plod on regardless. So we'll generate our predictions the same way we did before using the predict function. And I have now some new predictions. Well, I'm going to combine the test data, that data frame, with my model predictions. And by the way, in case you're interested in what model predictions looks like, oops, that was added as a markdown line. There we go. All it is just essentially an array of values, an array of prediction values. So I need to turn that into a data frame, combine it with my other data frame, and get outcomes too. And this is what I get. So my duration, 19 seconds, my predicted duration, 20 seconds. My predicted throughput, 2.01 versus 1.90. So that's a little bit different, but not too big of a difference. If I focus on durations, 203 versus 199, 122 versus 127. Again, the eyeball test is saying, we're like 5 to 8 seconds off per prediction. So nothing here stands out like the 19 to 81 second prediction in the first go around. But I am also just looking at 6 rows. And again, eyeballs aren't going to give me the full answer. So let's look at root mean squared error. And that says for duration, 10.75 seconds. So now instead of being off by 26 seconds, I'm off by 10 seconds. It's a significantly better difference. And now we're talking about maybe I'm off by 5 to 20% instead of 20 to 100%. If I plot this like I did before, what I mentioned was, hey, in an ideal world, in that ideal world that I keep talking about, but that we'll never have, every dot is on that line. Well, what I have in practice is we're kind of bouncing around the line, sort of like I mentioned, and I have a couple of outliers. So these outliers, the predicted duration minus actual duration, these things are, maybe we predicted that it's going to take 20 seconds, but it actually took 90 seconds. So in those two cases, most likely what was happening was I was doing something else on my PC at the time, and that ended up taking resources that weren't being taken during some of these other tests. I believe there was an NFL game on that I was watching at the time. So there's a possibility that these two tests were impacted by the observer deciding to use the computer for other things. Nonetheless, I'm pretty satisfied with these results. They are bouncing around 0 a lot. I do have a couple of outliers that are still real data. That's how long it really took to back up that database. There may be some external influence on there. But if I scroll up just a little bit and kind of ignore those outliers for a moment, on the whole, we seem to be doing a pretty good job. And as databases increase, we're not seeing a shift like we did in the first model. So that's a really good sign. Now, I'll take a couple of minutes and decide, well, how can I translate this from I have a model to what values should I actually choose? There are a couple of ways to do it. One is that we could try filling in different inputs, and we could try saying, well, let me look at the different values of buffers and fix block size. I'll fix file count. I'll fix database size. So this is actually memory utilization. buffers times max transfer size. And we can build predictions off of that so that with different memory utilization, we can see this is how many seconds that we expect the database backup to take. So as that number goes up, we can see that we start in the 64 to 66 range, and then at about 120 megs, it drops down to 58, and it keeps dropping until we get to 4 gigs, after which point, no matter how much more RAM I add, it's saying it's going to take the exact same amount of time. This is not necessarily going to be true. What's happening here is that random forest builds out those decision trees, those if-else statements. And basically what we're ending up with is that, we're kind of in this little branch, and that little branch says, all right, well, if your memory is greater than or equal to, whatever this amount is, then we're going to predict this many seconds. So that's what's happening. Basically, random forest, because we only trained on values up to this point, it makes no judgment on what might happen outside of the area in which we trained. So if I add an order of magnitude or 2 orders of magnitude more RAM, it doesn't know how to solve that problem. All it can do is say, based on the data that you have given me, on the parameters that I've received, this is what I can make as a reasonable judgment within that parameter. Other types of regression, like linear regression, can make these what are called out of boundary speculations, but there's a huge risk in it because you're out of the boundary of what you would normally anticipate or what we have actual data around. So those out of boundary guesses are judge those a lot harsher than you would the in boundary guesses. Like I don't trust what a linear regression prediction would be if I had 10 times more RAM, because I don't have any data that tests it, that confirms what those values look like. So the operating model probably is not the same at 40 gigs of RAM that it was at 4 gigs of RAM, is what I'm getting at. All right, so we can certainly do a lot of that kind of poking around and seeing what the results look like. But I've got a better answer for us. That better answer, kind of reverse the process. So instead of performing our analysis and getting back, here is the end result, here is the prediction based on these inputs, what I'd like to do is say, what are the set of inputs that minimize my output? And so let's do that. We're going to use a function called EV-tree. EV-tree as an evolutionary tree. It is if I remember right, this actually does use genetic algorithms, which I've got a whole talk on because I love genetic algorithms, despite the fact that neural networks basically wipe the floor with genetic algorithms in most cases. But, and even before then, support vector machines were better, but I've still got a love for genetic algorithms in my heart. So we're using this library. This builds out what are called evolutionary trees. And the idea is it's sort of like random forest, except that we're going to learn from the process of building these trees and build out a whole series of new trees. And as we're learning from these processes, we can also figure out what the parameters are on those inputs. Building EV trees takes a little bit longer than regular random forest, although for our data set, it did finish. And I can visually interpret these trees and get a visual that looks a little like this. So what this is saying for my data is, this is database size in gigabytes. If our database is less than 50 gigabytes and our memory usage in megabytes is less than 32 and our file count is less than 10, then we expect that the throughput, seconds per gigabyte, will have a median of that black line, will have the middle 50%, the interquartile range will be this box. And this is our expected range. We're just slightly above 2, but there's the occasional extreme outlier. And so I have these different trees that are using subsets of the data and are giving me results for number of seconds per gigabyte. So if I go through here and I have less than 10 files, then my median value is somewhere around there. But if I have at least 10 files, my median value drops. So what this tells us is if I'm a small database and I have a small amount of RAM, it actually makes more sense to have more files because my throughput, my seconds per gigabyte, is lower than if I have fewer files. So I can read and interpret this graphic that way, or alternatively, I can just type EV and get a textual tree that gives my results a little bit clearer in this case. So for a relatively smaller database, that's going to be 50 gigs or less for my data. What I'm looking for is what is the smallest value of throughput? And it's this case where memory usage is greater than or equal to 32 megabytes. That's better than less than 32 megs. So what this is telling me is for those smaller databases, I want to have at least 32 megs of memory utilization, 32 buffers at 1 megabyte max transfer size. That's going to give me my best results. I could have more than 32 megs, but it's also telling me I don't need more than 32. I am not getting a major benefit from having more than 32. So for this database size, I just want to have 32 buffers. If my database is more than 50 gigs, or at least 50 gigs, then I perform the same analysis and I say, I want to have 120 buffers at 1 megabyte max transfer size. And that's going to give me my best throughput. So if I do the same type of prediction, get my predicted seconds per gigabyte, I calculate out what my expected duration would look like, and I look at these results. Again, my duration is 19 seconds, predicted 22. So eyeballing these, there's some difference, but it's within relative values of reason. I perform my root mean squared error. It's about 11 seconds per of error per test. So slightly higher. If we go back up here to the random forest example, we were at 10.75. If I check out here, we're at 11.29. So about half a second worse, which means this isn't exactly the same model, but it's pretty close. If I generate this plot, here's what we have. Now, here's my value of 0, and we can see that we are bouncing around, but we also see these lines. And when I see lines like this, what this indicates is our model is probably missing some important piece of information. That piece of information is what is driving the linear relationship. What I should be seeing is dots kind of bouncing around randomly, that we don't have a necessarily strict linear term. We do see somewhat a little bit of this kind of moving down, that as duration increases, the expectations kind of, we're undershooting them a little bit. The end result, what this implies typically is your model is missing some bit of information, some explanatory variable that would help remove, like it's included in the noise, the excess, but there's actually something there that you're missing. And what I anticipate the answer is that this model is only using memory utilization. It's not also using file count in most cases. And that is probably what is happening here. So what we're ending up with is that, well, we're probably not taking the best advantage of file size if we have the combination of this 120 megs of memory and additional files. Then we turn this from, you know, a line into more of just random jitter around the 0 mark. But the way that the evolutionary trees are built, based on the number of samples that we have, we purposefully limit how deep the tree can go, which means that it really only is taking advantage of 1 to 2 features instead of really trying to dig into all of them. So that's my interpretation of why the result looks the way that it does, but that even with the way it looks, we're still getting some good insight that, all right, on this hardware, if I have a database that's more than 50 gigabytes in size, I'm going to use, if I'm using Ola's script to back up databases, or Minionware, Minion Backup, or if I've written my own, if I'm using DBA tools, whatever tool I'm using to back up those databases, I can say for these databases, I'm going to use this setting of 120 megabytes, so 120 buffers. For these databases that are smaller, I'm going to use 32 buffers. So that's what I'm getting out of this analysis. I'm getting back to what those inputs were for my databases and grouping it in the sanest possible way. So wrapping up the talk, we covered a data science scenario that I think is practical and pertinent to database administrators. Tried out a couple of different algorithms, random forest as well as an evolutionary tree, and saw how they compared. If you want to learn more, if you want to grab these slides, if you want to get links to additional information, if you'd like to get the demo code, that's all at csmore.info/on/backups. If you do have questions afterwards, please do feel free to email me or message me on Twitter. And with that, I'll open the floor if there are any questions. Otherwise, I want to say thank you.
That was absolutely amazing. I wish I knew more about this topic, because I don't think you know how many hundreds of hours that would have saved me over the last few years. But I can promise you I am going to be watching the session about 3 times. I'm probably going to be blocking off my weekend here so I can learn more about that. That's awesome. Thank you.
Thanks.
Yeah. Do anybody have any questions? And throw them in the chat window when you can. And bottom line, if you're watching this on YouTube after the fact, his contact info is up on the screen here. Please do not hesitate to reach out to him. Just like everybody else, hopefully in this community, we're more than happy to answer your questions. These topics are critical. They're not the most glamorous topics, but holy cow, you want to make your life better as an operational DBA, this is the stuff you got to do. Cool. Okay. Well, I don't think we have any additional questions. So, hey, thank you very, very much, Kevin. That was absolutely awesome.
Of course, it was my pleasure.
Very cool. So thank you all for watching. If you're watching this after the fact, make sure to check out more of the videos on YouTube. And with that, we will see you next month.
All right. Thank you.